So in this video, we are going to talk about the properties of arcs and the properties of chords and applying them. So the first blank is that a central angle is an angle whose vertex is in the center of a circle. So if we were to draw a picture, a central angle would just be something that goes to that centerpiece and makes an angle. So it'd be like that little angle right there. An arc is an unbroken part of a circle consisting of 2 points called the endpoints and all the circles or all of the points on the circle between them. So with this angle, you could have this arc right here, or you could also have this arc. Oops, that's not the pen I wanted. Or you can have this arc around, and there are two types. So, two types. The first one is a minor arc, which is the pink. So if we come down here, a minor arc are the points on or in the interior of a central angle. So like I said, it's just this little bit right here. And the measure of a minor arc is equal to the measure of the central angle. So just keep that in mind. If that angle was 30 degrees, then the arc would also be 30 degrees. A major arc is an arc whose points are on or in the exterior of the central angle. So if I have this central angle ABC, my major arc is actually going to be all the way around the circle, and you're going to have to subtract from 360. So if that angle was 30 degrees again, you do 360 minus 30, which would be 330, and then your major arc would be 330 degrees. If the endpoints of an arc lie on a diameter, then the arc is a semicircle. And the measure of a semicircle is always going to be equal to 180 degrees. So if you notice here, that EG goes through the center of the circle, and it's half of the circle, so it'd be a semicircle. Now, with naming arcs, minor arcs are named by 2 points. Major arcs and semicircles must be named by 3 points. So when I talk about the major arc up in this table, it would be EFG, because we have our endpoint going to a point that's outside and then another one. And then with the minor arc, I just need to say minor arc AC. And the reason behind this is because if I'm looking at the top two between the minor arc up here and the major arc down here, with the minor arc, if I say AC, I'm just going straight from A to C. But if I have this major arc and I want to talk about it, if I say AC, most people are going to think I'm in the middle. So I have to specify A, D, C. So with this first one, we have the circle graph that shows the types of grass planted in the yards of one neighborhood, and we want to find the measure of arc KLF. So if we look at it, because it has 3 letters, I know it's going to be a major arc. So from K, oops, not in draw, there it is. So from K to L to F, okay, we want to find what is that measure. So because we're trying to find the measure, it's going to be the same as the angle right here. And so in order to do that, I know that this full circle is 360 degrees, and I'm looking at 65% of my full circle. So in order to find the measure of my arc, I know it's going to be equal to the measure of that angle. And so then I would do 360 degrees times my percentage, which we write it as a decimal, so that'd be 0.65, because we're just looking at 65% of that circle. And so then that gives me that the measure of arc KLF, don't forget the little symbol, is 234 degrees. And again, you're just looking at total degrees in a circle times the percentage of the circle you have for these ones. So looking at this music sales, we want to find the measure of angle FMC. So FMC, go from F to M to C. So it is these three sections. So if you notice with these three sections, I have pop, country, and R&B. So because I have three sections, I still need to multiply my full 360 degrees times the percentage I need, but because I have three sections, I'm going to have to add all of them. So some of you may prefer to actually add them and then put it in. For me, I'm just going to put 9% is 0.09 plus 10% would be 0.1 plus 11% would be 0.11. And so then when you multiply that out, and actually I didn't write down what it was ahead of time, but if you were to actually add them, this would give you 360 times 0.3 or 30%, and 360 times 30% is 108 degrees. And that makes sense because you can use whether or not the angle is acute or obtuse to kind of help you estimate. So because this angle is obviously bigger than 90 degrees, I know it's going to be slightly bigger than 90. So to find the measure of arc AHB, use a different color. Oops, I thought I was going to use a different color. So AHB goes from A to H to B, and this is an arc, so we're actually going from A to H all the way around to B. So it's actually most of the circle. So you could go through and add all these little pieces together, but because I'm missing this 25% right here for rock, I know that the rest is 75%. So if I do 360 times 0.75, that will give me 270 degrees. All right. And then to find the angle of EMD, let me grab, let's do the pink. Angle of EMD, E is here, M to D. So we are really, and actually that color did not show up nearly as well as I was hoping, but it is actually this little slice right here. So looking at that, it is country, which is 10%. So we would have 360 times 10%, which would give us 36 degrees. And again, that's just for the central angle there with that arc. Okay. So adjacent arcs are arcs of the same circle that intersect at exactly one point. So RS and ST are adjacent arcs. Remember, just like with trig, adjacent meant they were next to each other, so these arcs are just right next to each other. And the reason why we have these adjacent arcs is because we can do an arc addition where you're literally just adding two little baby arcs to make one big arc. So just keep that in mind when we talk about arcs, that you can add them together to get the full size. So we want to find the measure of arc BD. So looking at the arc BD, I'm looking right here. Some of you may be wondering, why am I not going on the outside, so going this way? And the reason why is because I only have two letters. I know it's a minor arc, and a minor arc really can't be more than half of the circle, so I don't want to be going around the big side. So in order to find the measure of BD, you're actually going to have to use some of your supplementary angles. So you notice with this 97.4, it makes a straight line all the way across. And so it's actually supplementary to the angle next to it right here. So if you do 180 minus 97.4, you get 82.6. So I know that this angle is 82.6 degrees. So then if I want to figure out what this angle is right here, because again, we're looking for that BC, but I can't really do much with it right now, then you could also subtract from 82.6 to get that this is 30.6. Because again, these three angles would all be supplementary to each other. Now, some of you may have been even smarter than I am and noticed, hey, wait a second, I see an X right here. And if you recall, when you see an X with angles, those are vertical angles. And so we have this angle here and this angle here, which means BC, or the angle, is going to be 97.4 degrees as well. And again, you can double check it with supplementary angles and stuff if you want. But because the interior angle is 97.4, I know the measure of my arc is also 97.4 degrees. Okay. Oh, wait, I'm just kidding. Haha. BC is 97.4, but because I want BD, hold on, let me change my measure of BC is 97.4, measure of arc CD is 30.6. So when we add them together, because of our arc addition postulate, we would have 128 degrees. Whew. Almost messed that one up. So just a quick recap in case I confused you. To find all of these extra angles, and let me get rid of some of these extra fluffs. I used vertical angles to determine that angle BFC was the same as angle AFE. And then I used supplementary angles to figure out that angle CFD, this lime green one, was complementary to this 52, which would have been supplementary to the 97.4. So then when you add the degree measures of the orange central angle and the green central angle, then you get 128 degrees. So within a circle or congruent circles, congruent arcs are two arcs that have the same measure. So in the figure, arc ST is congruent to arc UV. And you notice that both of their central angles are x degrees. So these arcs are going to be the same as well. Okay. So into some theorems. If you want to put the numbers, you can. You don't have to though, but this is 12-2-2 in the book. But in a circle or congruent circles, congruent central angles have congruent chords. So if we have that angle EAD is congruent to BAC, I know these are congruent angles. And the conclusion that I can draw from that is that the chord DE is congruent to the chord CB or BC, depending on how you want to write it. So congruent angles have congruent chords. Oops. Why is it not erasing? There he was. Whew. And I'm just writing the shorthand congruent angles, congruent chords, because it'll come in handy if you're just trying to look real quick at what the rules say. So the next one, congruent chords have congruent arcs. They tell us ED is congruent to BC. So I have congruent chords. And with these congruent chords, I know that arc ED is congruent to arc CB. So again, congruent chords make congruent arcs. So then, last but not least, we have congruent arcs have congruent central angles. So we know that ED or arc ED is congruent to BC. So that's our congruent arcs. And because those are the same, then I know their central angles are what the arc goes to. So angle DAE is congruent to angle BAC. So congruent arcs make congruent angles. All right. So going on, flipping the page. With example 4, we want to find, or we know that chord TV is congruent to chord WS. So we want to find the measure of arc WS. So this goes back to the theorem we had before, which we have congruent chords. And with congruent chords, looking back, we know that we have congruent arcs, which is the second little part right here. So congruent chords, congruent arcs. So if I know that these two chords are the same length, then I know that their two arcs should also be the same. So because these arcs have these values put to them, we can just set it up as an equation. They are the same, they're equal. So 9n minus 11 equals 7n plus 11. So when we solve, I would personally subtract the 7n first so that I have all of my n's together on one side and they're positive, which is just a bonus. So then we'd have 2n minus 11 equals 11. And then we have to add 11. So we'd have 2n equals 22. And then when we divide by 2, we get that n equals 11. Now, because these arcs are congruent, it doesn't really matter which one you plug into, but if you want to just be consistent because they're talking about arc WS, then arc WS is 7n plus 11. So you plug in your value for n, which is also 11. Boop. So then we'd have 77 plus 11, which is 88. And again, this is the measure of the arc. So measure of WS is 88 degrees. Okay. And again, if I were to have a central angle, and this is just to tie more in, my central angle would open up to the arc, and that central angle would also be 88 degrees. Okay. So example 5, we have circle C is congruent to circle J. So we know they have the same radius. And we know that GCD is congruent to NJM. And we want to find NM, which is this chord right here. So if we go back to the theorems we have congruent angles. And congruent angles tell me that I would have congruent chords, which is number 1. So because I know congruent angles make congruent chords, I'm going to come back down. Whoop. Congruent angles have congruent chords. Oops. So just like we did in the one above, we're going to just solve the equation. We have two values that we can just set equal to each other because these chords should be the same length. So we'd have 14t minus 26 equals 5t plus 1. So we would subtract the 5t first, which gives us 9t. And then we would add the 26. Oops, got ahead of myself a little bit. And when you add 26, you would have 9t equals 27. So then when we divide by 9, we get that t equals 3. And so then, just like before, you can technically plug it into either of them. But because we're looking for NN, NM, I'm going to go ahead and just plug into that. So that would be 5 times t, which is 3, plus 1. And so then when you plug that in, that would be 15 plus 1, which tells us that NM is 16. And if you plugged it in to the other one, you would get the same result as well. So our next one, if you want the theorem numbers, it is 12-2-3, and this one is 12-2-4. Again, these are just numbers that the book assigns, so don't feel like you have to memorize them. But with the first one, in a circle, if the radius or diameter is perpendicular to a chord, then it bisects the chord and its arc. So if you notice with CD, it is perpendicular to EF. So I know that it bisects EF and arc EF. Okay. Now, if the perpendicular bisector of a chord is a radius, the perpendicular bisector of a chord is a radius or diameter. So because this chord got bisected and it's perpendicular because of that 90-degree angle right there, then I know that JK would be a diameter of circle A. If this only went to like A2K, then we would know that AK was a radius for this circle. So, applying that, with example 6, we want to find NP, which is the full length of the chord. And they tell us that RS is 8 and SM is 9. So one important thing to remember is that with that theorem, this chord is bisected evenly, but the piece that is cutting through the chord, that RM, may or may not actually be bisected. So in order to do this, you're actually going to have to use right triangles, yay! But rather than using trig, it's actually just Pythagorean theorem. So if you notice, we really just need to know what is the length of one of these sides. Because if I can find one of them, then all I have to do is double it. So if I want to find the length of this orange side, I can actually, from my center of my circle, draw in a hypotenuse, because now I have a radius from R to P, and that radius would be the same as RM, which is 8 plus 9, so that is 17. So I can gather that that is 17 by adding what the other radius was, RM. So then we're just using Pythagorean theorem. So A squared plus B squared equals C squared. And I know that one of my sides is 8 squared, that's RS. But I don't know what my other leg is, so I'm going to leave that as B squared. And then my hypotenuse is 17 squared, because that is RP. So then 8 squared is 64. And 17 squared is 289. So then when we subtract the 64, we get that B squared equals 225. And then when you take the square root of both sides, you get that B is 15. So that means B is really that one little section of this. It's the orange. So because my orange section is 15, now I just have to multiply that by 2, because again, it's bisected, so that's half of it. So I know that NP is 30. So that is our final answer. And I'm trying to think of how I want to make it more obvious. There, since I had to use the highlighter. So our final answer is that NP is 30, because we cut that in half. Okay. For this one, we want to find ZY, and we are going to round to the nearest hundredth. So just like the last one, I know that ZY is cut in half by WX, because WX is a radius, and it is perpendicular to it. So because of that, just like I did before, I'm going to make myself a little right triangle right here. Because I can find that radius just by doing 12 plus 28, which is 40. So I know that this radius is 40. So then you're again using Pythagorean theorem. A squared plus B squared equals C squared. One of my legs is 12, but I don't know the other leg because that's our missing piece. And then my hypotenuse is 40, so then it'd be 40 squared. Remember, C should always be the hypotenuse. So then when you do this, that would give you 144 plus B squared, and 40 squared is 1600. So then when we subtract 144, we get B squared equals 1456. And when you take that square root, you get that B is 15756. So I'm just going to make it 1576. So then to get my full length, because this is only half of it, we're going to multiply that by 2. So then ZY equals 76.315 which really, if we were rounding to the nearest hundredth, we need 2 decimal places. So this 1 would look at the 5, which tells it to round up. So it'd be 76.32. Okay. And so your homework is on page 806, numbers 1 through 28, 31, 38, 39, and 51. So if you have any questions, just let me know.